Hello everyone. So we are back to measure theory, and this time, rather than being a bit abstract, I think I will be a bit more practical in this video and try to explain it something slightly differently. Because most of the times when you are, let's say, watching the videos on measure theories by, there are lots of channels which do these things, but most of it is maths which is very abstract. And although abstract maths is good, it gives you some idea of how to, let's say, solve problems in the real world, but initially starting it is a bit challenging. So here my goal is to put the concreteness here and try to visually give the intuition how it works. And Julia probably is one of the best ways to do it because it's very simple. So you can see some of my previous videos in measure theory, which were quite abstract. This one will be this one will be more example based. So here you can see, here I'm just writing the formula here. Let me just hide this out. So here, again, going over the notation one more time. Basically, you can see it in the previous video also. W is the number between 0 and 1, so it can be 0, 0. It cannot be 0 actually. It can be 0 0.5, 0 0.25, 0 0.55555, whatever. And all this can be generated by this sequence, just by the summation. And I can have AI can be only 0 or 1. All I need is this, and using this infinite, I can generate anything here. But you don't have to believe me. I mean, for now, I will try to show you how this works. So, for example, if I write this function here, and then let's say, call this map sequence, basically HT produces a number, right? So this HT, you can think of it as, instead of HT, I can say this is 1, 0, 1, 0, 1, 0. But for now, I have written the function like HT. So you can think of this as the sequence of A1, A1, A2, A3, A4, A5, A6. So all the sequence, it is just mapping this into a different pattern. It will just give a number, right? All the numbers will be between 0 and 1. And to make sure that it doesn't give, two sequence won't be mapped with the same thing. But there's a problem. What if the sequence is like this? This gives 0.5. And what if the sequence is something like this? This is, as I keep increasing this, it will go closer and closer to 0.5. But if I check this sequence, this is 0.5. This becomes a problem. So basically, my rule is that whenever I have a number like 0.5, I will always map it to something like this sequence, not this one, because t is all zeros, right? So basically, first of all, first rule, if 0.5 is mapped to two set of sequences, I will prefer the non-terminating one, which is something like this convergent part. And second rule is that if there are some sequences like t to t, For example, if I have something like t, this, and then it will be 0 because these are all going to 0. So basically, all these sequences won't be represented properly, right? So that's why we are skipping all the sequences which are like having these. But there's a finite number of them, so it doesn't matter that much. Anyway, the first idea was to establish a mapping, which I have already done using this function, which is simply what I have written here. Now, coming to the sequence part. Here, okay, I'm just hide this, just to make it simple. Okay, and here, for example, this one. Okay, so maybe this variable, I use it here just to make it easier. Number of tosses. Okay, so if there's one toss, nothing happens. If there are 3 tosses, let's say this, 4 tosses. See, this is mapped to this is mapped to this. All the numbers are getting mapped, and you don't see any number which is like having like any sequence which is mapped to the same number, right? So this is working. I can even go to 5, 6, 7, and I mean the threes will keep increasing, but you will see that this is the mapped sequence, right? So it makes sense. And I can even plot this, but for now, not needed. So this is just a way of testing our mapping, that mapping is working fine. So let me give an example here. In Rademacher functions, last time we were going through this was, I just plotted it really finely. So if I say that this is for Rademacher, let's say 3, this means that for coin tosses, what are the chances that I will gain money at the end of 3 tosses? So, for example, just to make it super clear, I will probably say something like this. Let's start with 1 actually. It's a very simple case. This means that if the numbers are landing here, means I have the sequence something like this. Otherwise, I have the sequence something like this, right? Similarly, if I have this, then there are different cases. And tails means that I lose $1, heads means I gain $1. But I'm not just counting the heads and tails here. When there are 2 tosses, what are the possible choices? There are 4 possible choices. You easily do that. You can do the HT combinations like 1, 2, 3, 4. But as this grows bigger, this becomes difficult to do, right? And there are not many combinations to process. If you are able to map this sort of thing in this space, for example, it gets really messy here. So if I go to 6, maybe 7, then it gets fine, and by 9, I guess you can't even notice it, right? So anyway, the idea is that if I can map this, then I can measure the probability by just measuring the length of this, because I've already mapped everything here. And that's the whole intuition behind mapping the events to a number space. That's why the measure theory is so important, because it gives you a mathematical way or a numeric way to calculate the probability. And it is more rigorous. So just to give you more examples, I mean, for example, if I, okay, if I just look at the mapping, So if the number of tosses are 3, this is getting mapped here, HHT is getting mapped this. So all these mappings are different, right? And this is nothing but 111. If you, let's say heads is 1, then 110, 101. So why am I mapping this? One of the examples is the gambler's ruin problem, where if the event is something like, if I play the game for a long time and I start with $1, what are the chances that I will go bust in the first move, or in the second move, or in the third move? Note that when I say for the first move, it is very easy to see. It is 50%, because either you can gain $1, which is 1 plus 1, or you can go bust, which is 1 minus 1, right? So either you gain $1 or you lose $1. 1 minus 1 means that you lost, and the chances of ruin are 50% here, right? Now, what happens if I go to second toss? If I want to calculate the probability of ruining in the second toss, I want to deflect the probability doesn't happen in the first toss. Similarly, for the third one, I want the ruin not to happen in the second toss and the first toss. And you will think about conditional probabilities, it becomes complicated. But if I think about areas, it is very simple. I can think of something like this. If I don't want the ruin in the first event, I want my space to lie here between 0.5 and 1, right? And then if I don't want this to happen in the second event, I want it to lie somewhere here, because the first one already told me that it has to be here. Second one is telling me it has to be here. So it is the intersection between this and this. What about only in the third one if I want the ruin to happen? Means this was the area which was common. Somehow this part. So this should be roughly 12.5%, which means that the probability of losing all the money in the third toss and no other toss is 12.5%. It is very easy to see intuitively. And this is how you can visualize it. Same thing I'm doing. I did that, okay, if I choose the number of tosses, for the first toss, I calculated this set. And then for the second one, I calculated that, okay, I don't lose. And just for the ruin event, I mean, for the third one, when the ruin event happens, I want it to lose. And I keep taking the intersections of the sets just to get the final result. And final result is nothing but my plot of values, which says the probability. So chances of ruining in exactly the third point, or in another way asking, what is the chance that the game will continue up to plot, or the third up to the third toss? It is 12.5%. If I were to say maybe till 10, let's say, you see all the values are still unique. You have so many combinations being produced. And last one, yes, this cannot be mapped, as I discussed earlier. And see, the probability is very low here, right? So it will be close to 0. And maybe I think I can print the result also, just to be okay. So maybe print ln, because it doesn't make sense. So this is for first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and see, it's a very small number, 0.0009, right? So you will be really lucky if you were to have this game continue till the 10th toss, right? And The good part about this puzzle is that you can play around with the numbers and kind of establish the intuition in a much more concrete way. So I hope you see why the mapping is important. I mean, the whole part of measure theory is to write the event in terms of this mapping and then easily establish. So, for example, what puzzle we solved was something like this. I'll just write the expression just to be W belonging to, which is I think mostly written as epsilon I, where I is, or I will write something like this. This, where I am saying that S is S A mega, and this is greater than minus 1 for L less than K, or number of tosses, okay, and S, which is sum of tosses, K, sorry, omega equals to minus 1. Hopefully it comes out correct. And okay, and just to add one more space, let me see. Yes, so this is my basically my set, and okay, maybe it will appear using this. Okay, fine. So W belonging to, or omega belonging to 0 comma 1, where my S is nothing but my summation of the total amount won or lost for any L tosses is greater than minus 1, where L is less than the total number of tosses. Total, okay. Okay, total number of tosses, and your SKW, which is if they are K tosses, let's say, then this is equals to minus 1. This is the event which says that the gambler's ruin will happen at this toss. And once I know this event, it is very simple to model this. This whole formula has been modeled in simple code. But once you read it, initially it sounds a bit complicated and doesn't make sense. So always the big advice in measure theory is that you try to code out the things that you are doing. And the simple mapping is a very, very fast way or very easy way to kind of get the intuition of this whole of this concept. If you stay abstract, then you will miss out most of the scenarios and you will be able to test it out. So hopefully this gives some idea on why measure theory is useful and why it is one of the basic things to know before jumping to probability theory and trying to solve problems. Hope this helps.